Hey guys, in this video, we're going to talk about solving right triangles by using the Pythagorean Theorem. We're going to talk about what the Pythagorean Theorem is, and then we're going to do 5 examples, including a word problem. So let's get to it. In order to understand what Pythagorean Theorem really is, we need to understand a little bit about ratios and proportions. Now, I've covered proportions in a previous video. Pythagorean theorem is often referred to as a squared plus b squared equals c squared, but that really does not do the theorem itself any justice. So let's talk about what's going on here. So let me focus on this c squared for a second. If I could find the area of a square, the way I would do that is I would say either side times side or a equals sides squared. So, for example, if the length of this side of the square is, let's say, 5, that means each side is 5. And then I would place that into my formula, 5 squared, giving me an area of 25. Okay, so how does this relate to Pythagorean theorem? Well, what Pythagorean theorem is saying is, if you create a right triangle and then place squares around each leg and the hypotenuse, you will be able to find the missing sides. But you can also use Pythagorean theorem to figure out if your triangle is in fact a right triangle, because the theorem only works with right triangles. My opinion is that the ancients used this square process, finding the area of a square, to actually figure out if when they were building something, if their walls and sides were actually perpendicular. Because when you're building with things like stone and marble, if things are not perfectly perpendicular, you kind of have a problem. So that's a little bit of history about Pythagorean theorem. What has happened over the centuries is it has been reduced to what we see as a squared plus b squared equals c squared. That is definitely not its original conception. Pythagoras is often provided with the credit for discovering this theorem, but the ancients have been using it way before he was alive. And if we know anything about Egypt, they built those pyramids, which were definitely contributed to the use of Pythagorean theorem to get perfect. So let's take a look at a simple example. If I called this length here 3, I call this length here 4, and I call this length here 5, that means that this is also 5, this is also 4, and this is 3. Well, I could plug this in, and to Pythagorean theorem, I could square or find the area of the individual squares, and then see if I get equality. What I can also do is I can solve for a missing side in doing so. So in other words, if I don't know one of my sides, I can find it using Pythagorean theorem, only assuming I have a right triangle. So let me just model this up a little bit, and I'll change this length to 6. Okay, so now I'm going to plug this into Pythagorean theorem. And this will be 9 and 16, and that equals 36. So now this is 25, which does not equal 36. So in this scenario, this triangle is not a right triangle because Pythagorean theorem doesn't work. There are a number of uses of Pythagorean theorem. Pythagorean theorem is huge. This ratio that exists amongst the sides can be applied in a number of places. In fact, throughout my math education, I have been shocked about how many times Pythagorean theorem has come into play. Okay, let's take a look at a couple of examples. This first example is a straightforward example of Pythagorean theorem and represents most of the type of uses of Pythagorean theorem that you will see in the middle school and high school setting. Finding the missing side of a right triangle is amazingly useful when constructing something. And Pythagorean theorem is a very good tool for that. The simplest way to use Pythagorean theorem is in the a squared plus b squared equals c squared form. What I am going to do is I am going to label the sides of my triangle. There are three parts to a right triangle: a pair of legs and a hypotenuse. C is always the hypotenuse, and A and B are the pair of legs. A and B is a little bit misleading. It's suggesting in a way with our alphabet that those letters need to be in a certain order, and they do not. Another way to write the Pythagorean theorem would be L squared plus L squared equals H squared. And I have seen that written like that a few times, but it's not very common, and it's part of the reason why we're not covering it that way in this video. So what I am going to do is I am going to label my triangle A, B, and C. I'm going to draw an arrow straight out from my right angle, and that is the hypotenuse, or C. From there, I can label the other two legs however I choose. I can label A and B here, or I can label this B and that A. Pythagorean theorem does not know the difference. The other point to this that's very important is that this is addition. And addition is commutative. So that means that really, if we wanted to, we could rewrite the Pythagorean theorem like this. I am spending so much time on this part of the Pythagorean theorem is often because these are the questions that come up. Now that I have everything labeled, let's solve the problem. I'm going to plug into the theorem 8 squared, then 6 squared. If you watched my video on Pythagorean quadratic formula, it's a very similar process. Now from there, 8 squared is 64, and 6 squared is 36. We have to follow the order of operations, so you cannot skip these steps. 64 plus 36 equals 100. I'm bringing down the x squared. Notice I'm keeping that x squared on one side, similar to as if I were solving an equation. Now I have to square root. So the way I undo a square is I square root it. So in other words, 5 squared is 25, and then if I square root it, I end up back at 5. So they undo each other, getting the x by itself. And the square root of 100 is 10. That means the length of this triangle is 10. This is also called the Pythagorean triple. So if you would have noticed in the definition of Pythagorean theorem, or the explanation of Pythagorean theorem, I used a 3, 4, 5 triangle. This triangle, 6, 8, 10, is a dilation of that triangle by a scale factor of 2. Alright, let's take a look at the next couple of examples. Be careful as the orientation of the triangle changes. I always recommend labeling C first, then A and B. And now I'm going to plug in to the Pythagorean theorem. I've mentioned this in the quadratic formula video, that I often write the formulas out every time I use them. That's how I remember them. 12 squared is 144, and 13 squared is, which is 169 according to my calculator. Now I'm going to subtract the 144 to both sides. X squared equals, that looks like 25 to me. I'm going to double check that on my calculator. And I am correct. And now what I'm going to do is square root that square away. So x equals 5. That means the length of this side is 5. 5, 12, 13 is also a Pythagorean triple. There are a handful of primary Pythagorean triples, but then you can infinitely dilate them to create more Pythagorean triples. Okay, let's take a look at the next example. I'm going to start all of my problems the same way, and that is by labeling C. From there, as I keep repeating, A and B really don't matter. I just need to label the legs A and B. I'm once again going to write out Pythagorean theorem, and then I'm going to plug in my information. From there, we're going to get to work. The square root of 12 squared is 144. 14 squared is 196. And I'm maintaining equality, keeping that x squared. Now I'm going to add 144 and 196 and get 340. From here, I am once again going to get square root. This is once again, and I bring this up a lot in my videos, where a very good calculator, such as a TI-36X Pro or a Casio 115 ES or 300 ES, is really, really helpful because they have the math print function, which is super powerful. In this case, I did not have to simplify the radical, and I was able to get the answer to square root 85. Let's take a minute and talk about this. So the answer to the length of the hypotenuse is 2 square root 85. If, and I would not recommend it unless you had to, you wanted to convert this to a decimal, the answer is 18.4391 ... which is rounded. It is an irrational number. Historically, the square root symbol was designed to avoid having to work with long, non-terminating decimals. It's simpler to use than it is decimals. The reason why most students avoid working with square roots is not because they're necessarily harder, it's because they have less exposure to them. There is no reason to convert that length to 2 square root 85 unless the answer choices you have are given in decimals. Otherwise, I would leave the answer like that, and depending on your application, you may be able to keep it this way, or you may have to convert it to a decimal to different, let's say, decimal points. So, for example, if you're building an aircraft, I believe you typically go back about 4 to 6 decimal points. If I'm building a wood frame, I'll probably just go back 1 or 2. So the precision required is what dictates how you round here. Okay, let's take a look at the next example. So I just got off a pedestal about how square roots or radical numbers are easier than decimals. And let me show you how. So let me provide you further evidence. So for starters, we're going to go through the same exact process that I have a few times now, and now I'm going to plug in. So I'm going to place this in parentheses. This is how we square roots, and then I guess I'll place the x here, but I think I mentioned in the previous example you really don't have to. You could have left it C. Well, we talked about this. The square undoes the square root. So these are reciprocal or inverse functions of each other. So that's 5. Then 5 equals x squared. If I were to take the square root of 5 and convert it to a decimal, that would be 2.2361 and non-terminating. At what point do I square that to try to get 5 back? The answer is it becomes pretty difficult. So if I were to square 2.2361, I get 5.0001. Where I could avoid that confusion by just handling the root directly. Takes a little time to learn those rules, but once you learn them, you'll find math becomes a little bit more straightforward. 5 plus 5 is 10. I'm going to square root 10 now to undo that square. And I believe the square root of 10 does not simplify, which it does not. So I am just going to leave my answer like this, because this is the most precise answer. Alright, let's take a look at a word problem. Word problems for Pythagorean Theorem are not always representative of the best use of Pythagorean Theorem. But nonetheless, we really should cover them in our curriculums, and the reason being is because these word problems are very common in all sorts of standardized tests. So let's take a look at this one. A soccer field is a rectangle 100 meters wide and 130 meters long. The coach asks players to run from one corner to the other corner diagonally across. What is that distance? With word problems, we hear this all the time. Draw pictures. Well, I'm going to draw a rectangle. I do not recommend putting a lot of time into your picture. 100 meters wide and 130 meters long. Really does not matter in this situation which way you label your lengths. What is important is that I recognize that the player is running diagonally across, creating a right triangle. From here, I can use Pythagorean Theorem. If I finish labeling my triangle, this is 100 and this is 130. So you want to be careful about how you label it to make sure you create that triangle. And now I'm going to plug everything in. So I have a squared plus b squared equals c squared. I'm going to create very large numbers here. Or what I can do, definitely if I have a nice strong calculator, is I could just plug everything in at once. But for the sake of this video, I'll create the large numbers. And my calculator tells me that 100 squared is 10,000 and 130 squared is 16,900. Now I'm going to add these two together to get 26,900 equaling c squared or x. And now I'm going to square root it. As powerful as these calculators are, they will not give me this answer in some kind of radical form. Once the numbers get too large, they kind of pump them out into decimal form. The general rule for mathematics, unless you're told otherwise, is to go back to decimal points. So that's what I did. I got 164.01. I just want to show you a shortcut if you have a good calculator. What I could do is, instead of generating these large numbers, I could just square root both sides. In other words, I could avoid all those steps by square rooting and undoing that square, then bringing that square to this side. A large enough, powerful enough calculator will produce the same results. Which I paused the video just to check to see if I would have gotten the answer in square root form, and I did not. I got it exact form as I did doing this the long way. If you were to watch a bunch of videos of the practical use of Pythagorean Theorem, let's say in carpentry, this is typically how those folks use Pythagorean Theorem. Alright guys, I hope you guys have found this video helpful.